So now we're going to go over to the Applied Physics Lab and hear from Jim McAdams and Andy Calloway about the Messenger mission and some of the challenges they've faced.
Hi, everybody. I think we're just waiting for a couple slides to come up here. While we're waiting, I'll introduce myself. I'm the Mission Operations Manager for the Messenger mission. Started in 2002, a couple of years before launch, right around the time of the CDR phase of the mission, and then the Operations Manager since 2007, which took us all the way through the end of the cruise phase, through orbit insertion, and then into the 4 years of orbit phase operations. So I'm going to take a slightly different tack here. I'm going to focus more on the human factor and how operations is really focused on the human element. And one of the earlier presentations, it was discussed all the different possible career paths that a person can take in the field of space operations in general. So I want to keep that as kind of in the back of your mind the focus for this presentation. So we can go to the first slide. So I split my presentation into 3 slides. The pre-launch phase of a mission. A lot of missions have a cruise phase, so that was my second slide. And then for Messenger in particular, we of course had an orbit phase, so we'll talk about some of the challenges there, but all from the perspective of operations. So we consider ourselves, if you want to think of it graphically, as like the hub of a wheel, with all the spokes going out to the different elements, such as the mission design team like Jim here, the navigation team, ground systems, all the spacecraft engineers, and so on. So think about it that way. Right off the bat, when Jim was working with others to put together what the orbit phase would look like, they had decisions to make with what the orbit would look like. There's a lot of factors like allowing the spacecraft to cool down as it goes through its large elliptical orbit, and then also opportunity to turn to face the Earth to downlink the data and receive all the commands. But that could have been relatively arbitrary. And instead, working with mission operations, we came up with the scheme to have 12-hour orbits, and that was certainly intentional so that it aligned with the human day here on Earth. So pre-launch, Ops basically has the opportunity, which we're very glad of, and the responsibility, in fact, to shape and influence how we interface with the mission, especially one that's as long a duration as Messenger. For many years, if you made the wrong decisions, you have to live with the consequences of that. So it's very important in the pre-launch phase to take advantage of that. Everything from the types of commands and what they can do for you. It can be very annoying, for example, to have certain counters that you're not able to clear. It's just not part of the software. So that's all the kinds of choices we try to influence early on through the various software loads that are delivered before we even launch. So think about that when you're teaching the students about choices. Sometimes it can have far-reaching consequences. We also like to guide things like just the command and telemetry databases. The mnemonics that you want to come up with should be intuitive, especially a long-duration mission where you have maybe turnover many years later with new people coming on board. If you picked mnemonics that are intuitive and make sense, the learning curve is a lot less, and you don't have to document all the details that sometimes can be very tricky to dig through. So picking things as simple as a command that makes sense to turn on a component or to switch to a redundant unit or things like that are important. It's not uncommon for the early ops testing that we do. We have very large mission simulations where the whole team works together, as well as just individual component level tests. And all of those drive the changes to the flight software and even the ground software tools. And in some cases, the mission design. Sometimes there's a baseline mission design that sounds good on paper, but then once we get into the test, especially the mission simulations, you realize that it wouldn't really quite be safe to do things a certain way, and so we have the opportunity to maybe tweak it before it's too late. So think about that as well. And so Ops' early understanding of how all these features behave definitely drive all those. That's why pre-launch is so important. And there's always surprises that get uncovered, and hopefully most of those are uncovered pre-launch. But as you'll see in a few minutes, no matter how hard you try, there's always a few that you just simply didn't anticipate. And a lot of that's because the concepts of operations downstream for the scientists, for example, just aren't mature enough yet for you to make informed decisions on some of that. So we can go to the next slide, which was the cruise phase for Messenger. We had a 6.6-year cruise phase, as you heard, very circuitous route through the inner solar system with all those flybys. We had 5 deep space maneuvers and several other smaller trajectory correction maneuvers. And so we had to adapt to a lot of these special events that are outside of the day-to-day routines. The mission was optimized, as you can well understand, for operating at the Mercury sun distance. But in that early part of the mission, when we flew all the way back around to the Earth again, being that far from the sun, we had to do special things. We called them flip and flop maneuvers. Because of the power on board, we had to do that so that we could at times flip the spacecraft so that the backside was pointing to the sun. And that heated it up enough that all the different heaters would remain off so that you could conserve power. So those are the kind of things we had to do, especially because of that part of the mission, even though that wasn't the main design. So that was one thing we had to overcome. Another was these very large solar conjunctions. So occasionally where the spacecraft is on the opposite side of the sun from the Earth. And in the cruise phase, those could be very long. In fact, we had long ones in 30 and 40-day ranges. And so you have to do a whole new set of operations to accommodate that safely. And one of the things we did, for example, was to alternate rotations of the spacecraft back and forth at a certain cadence to help keep accumulation of momentum down. And that led us to other what-if ideas downstream, which ultimately led to solar sailing, which I think Jim will talk a little bit about. So what solar sailing wasn't something we had planned early on, pre-launch or anything, but we learned by doing these adjustments that, hey, why don't we use that into our favor rather than fighting against it? So sometimes it's an evolutionary process. It's not just something that all of a sudden you do. So you definitely learn along the way, especially on long-duration missions. And of course, the planetary flybys, that drove how we were going to operate on orbit. It helped us learn more about the planet itself and what kind of science we would take, and also how the instruments behaved, all the calibrations we did, all the way down to the little minute levels of the spacing between certain commands that we just couldn't have anticipated, on paper or while we were still on the ground before launch. So that's why you do all of these kind of activities to kind of fine-tune what you're really going to do. We also ended up doing several major flight software loads along the way, not just to the main processor, but I think every instrument had at least one, if not two, software loads to enhance and fine-tune how we would do things once we learned. One of the things we learned, we did these day-in-the-life tests and week-in-the-life tests in the cruise phase, and we learned that all the science that they wanted to capture required a lot of commands, and not just small ones, but the large types of commands. And that takes up physical memory space on board on macros. And so we realized we did not have nearly enough macro space to do the kind of science that they ultimately wanted to do. So again, because of that, we were fortunate enough to have a long enough cruise phase where we could reallocate the memory on board, for example, to have much more macro space so that we could get all that command volume on board for each week of activities. So that's just another example of something we never really envisioned until we got into the thick of it. So in general, very little of our pre-launch concepts of how we were going to operate in orbit actually made the cut, as you'll see in a minute here. So we can move to the last slide. In the orbit phase, we're 4 years now into it. We have several seasons that we work with. There's times where the RF signal from the ground and the spacecraft get occulted by the planet, for example. That's both a good and a bad thing. We also have thermal seasons, as you'll hear in a few minutes from Jim. We have twice a Mercury year, which is 88 days, times where we have to go over the hot planet and do various things like turn off heaters and rotate the spacecraft with the top deck away from the hot planet. As you'll see here, we have the solar panels on the spacecraft that we can offset each orbit of the mission. So these are all things that we kind of conceptually knew we had to do, but until we got into it, the mechanics of how to implement that routinely and safely took a while to iron out. So we work with mission design very closely to do all of these things, including placement of maneuvers. We don't like to do them what we call in the blind, out of contact. So we work closely with Jim to figure out exactly where we can place a maneuver and still have adequate coverage with the right elevation angle from the antennas, for example. Even in the last few maneuvers of the mission, we had just a couple weeks back an opportunity to tweak one of them and move it one orbit earlier to help some of the improved science, as well as give us a little more pad on the back end in case there's a problem. So we're always doing those kind of trades and working with everybody. Another thing we did to greatly increase the amount of downlink, the data that we could downlink, was what we call rate stepping, where we could take advantage of the specifics of each antenna's performance, the amount of noise, for example, from each antenna, as well as the elevation profile as it tracks through time, so that we would have a step function, several step functions for each 4 or 5 hour DSN track, rather than just an average straight line of downlink data rate across. So when you add that up cumulatively over weeks, months, and years, you can get a lot more data return. So we, again, conceptually knew we wanted to do that, but until you really get into how it works, you don't have those details. We also worked with science planning to pick things like consistent days of the week for things like momentum dumps. It's important in an orbital mission like this to have consistency, almost like a conveyor belt type of thing, where you can pre-plan what tracks the science is blacked out, for example. So those are all the kinds of discussions you have to have way early on so that you can implement it. And then as we got into it, we did things like automation. You can imagine, especially in extended mission phases, where you can't just keep doing business as usual. So incrementally, we were able to implement automation where we started off on weekends where the flight controllers could just observe the data from home, sitting in their living room with a laptop, and then ultimately enabling uplink so that transactions for the data downlink could be handled automatically instead of on Mondays, for example, when they came back in. So those are the kind of things you can do when you have a mission of this duration, where you can incrementally improve things. And then things like the DSN track durations. We went from 12-hour orbits just over a year after the orbit phase began. We brought it down to 8-hour orbits, again, for similar human factor reasons. But that changed everything. So then we had to come up with new schemes. We couldn't have a 5 or 6 hour track anymore to load a 4-hour command load. So we had a 3-hour track. So it obviously won't fit. So we had to figure out ways to split our command load safely into segments so that you could put up part of it on one load, and then on the next track you could put up the remaining segments. And you have to work around things like station handovers and momentum dumps so that when the commanding is turned off, you're not stuck in the middle. So those are all the kind of things you have to adapt to on missions like this, and I hope that gives you a feel from the ops perspective, being what we consider the hub of the wheel. As kids ask questions, what kind of career paths might I take? If they really like working on a team and working with all different aspects, touching each part of the mission at various phases, it's a great career path to choose. So hopefully I was able to convey at least a little bit of that. That's all I had. Thank you.
Is someone going to advance the slides too?
Did you join yours on this?
No, it's a separate presentation.
Just hit escape. It's on the desktop.
Anyway, while she's pulling that up, I'm Jim McAdams, the mission design lead engineer. I started in 2 weeks from now. It'll be 19 years since the first week of the first conceptual design of the mission. So I've been on ride along with a handful of scientists and a few others. So anyway, we talked about overcoming engineering challenges for the first Mercury orbiter. Next. Just a quick look at the spacecraft. It's powered by 2 solar arrays that are about 2.5 meters square. There's a large bipropellant thruster, 672 newtons or about 150 pounds force. There's a ceramic cloth sunshade that had to be pointed at the sun when the spacecraft is close to the sun to protect the sensitive components behind. You can see that here and on the 1/10 scale model that we have here of the spacecraft, so you have an idea of how big the spacecraft is. And there's multiple antennas. There's a phased array high gain antenna shown in the lower right, and then there are gimbaled or rotatable solar panels that are 2/3 mirrors to reflect the heat and keep the temperature from getting too hot. Next. So before launch, the big challenge was, now I'm the mission designer, trajectory and maneuver focus. So we had to find a trajectory that uses less propellant. We knew that this trajectory was demanding, and we knew that the spacecraft design would be an issue with, as it always is, but particularly for this, where we're going in so close to the sun that the always inevitable growth of mass of the spacecraft, but yet you have a fixed launch vehicle and launch speed, that you have to work with. So that margin would be shrinking, and we had to help them out and come up with a better trajectory than what we proposed to NASA. And so we had initially a 15-day launch period. Typically now you don't do less than 3 weeks. And we had a 14-day or 2-week backup launch period and a couple backup launch periods. And we had a 5.4-year trip to Mercury. And that was 2 3/4 kilometers per second of velocity change budget that we were counting on. And you can see the split there from how much was required to how much was for navigation, statistical, and margin. But our final result, what we launched at, was we were on the second backup launch period because of various schedule delays, things sometimes beyond the control of the project and sometimes under control of the project. So we launched on the 5th day of that second backup launch period, similar launch energy, and now we're going 6.6 years to Mercury orbit. And we saved over 20% in propellant in the velocity change from 2750 down to 2210 meters per second that we actually are getting out. We've already gotten out just over 2200 meters per second. So we're down to that final 10 in the upcoming couple months of the mission. And then the trajectory profile, there's a lot here. I just want to point out at the bottom, the scale shows we have the Earth gravity assist, that's 1 year after launch, and then we have 2 Venus gravity assist as you're moving in closer and closer to the sun with each of these gravity assist flybys, 3 Mercury gravity assist flybys at longer and longer duration apart. Now, these trajectories that are shown in the different colors that match down on the bottom, sometimes there are 3, 4, 5 on top of each other, so you cannot see them all. The Mercury flyby altitudes were typically around 200 kilometers, and our largest maneuver was orbit insertion, going into orbit on Mercury. Now, let's say one quick thing. The distance that we traveled was about 4.9 billion miles, basically going out to Pluto and halfway back just to get there. And we've since traveled like another distance from Pluto all the way back to Earth. We've gone around the sun since we've been at Mercury in orbit, that plus more. So we've flown around the sun dozens of times now, and we had about 16 orbits doing here. The distance that we traveled, the 4.9 billion miles, is roughly equal to, if you travel at highway speed, 56 miles per hour, for 10,000 years, never slowing up or whatever, then that's about how long we did it in 6.6 years. And one more thing, the 6 gravity assist flybys imparted between 2 and 3 times the velocity change that record holder from the spacecraft perspective, Dawn, imparted. We just borrowed it from the planets. So we did quite a bit more delta V, but only a small amount, 2.2 kilometers per second from the spacecraft. Next. And here's a view that is the solar rotating view, or the Sun-Earth line fix, meaning sun's in the center, Earth is always on the right, and it wanders in and out just a 1 to 2% because the distance from the Earth to the sun is different. This is actually a frame from the end of an animation that would take too long to show, but the same scale applies on the bottom, showing the different orbits in different colors. But here, you can see every one of the 16 orbits. Now, it's hard to pick them out, but it's whenever you're farthest from the sun. So you can see that little blue loop in the lower right, that's the first orbit. The next one ends at the top of that little loop where you're farthest from the sun. That's the end of the second orbit. And the third orbit is at the exactly on the left of the sun, where the yellow is farthest from the sun, and so on. So that's just an example. And then in the upper left, you see a 3-degree solar conjunction line, meaning the angle, the Sun-Earth spacecraft angle being 3 degrees and the spacecraft being on the opposite side of the sun. All those lines correspond to when the orbits cross in that area. And you can see just 1 or 2 times we went directly behind the disk of the sun, but not too many. We just got, when we got close, we had degraded communications, and we don't plan any course correction maneuvers. Next. So design challenge after launch. Mercury orbit insertion was the biggest, most important maneuver of the mission. And we initially had a plan for doing 2 maneuvers, about a 95%, 4%, 5% split. And these maneuvers would be a half week apart. The idea that from our early experience was we knew we needed a smaller maneuver, or we thought we did, to get a precise cleanup to really nail that orbit. And so that was the thinking. But we thought, well, as we get more confidence in using the thruster, it's not like Cassini where the first time you turn on that engine is when you're there for that test. We had 6 times to exercise that engine and got to know it well and its performance. So we thought, let's do it all in one maneuver. So that final orbit insertion design used almost 1/3 of the total propellant loaded on the spacecraft. We went into a 207 kilometer by 12.07 hour orbit. If a major anomaly were to occur during orbit insertion, we had put a lot of effort into contingency planning, and we had an excellent recovery outlook for full mission success within 5 years of the nominal plan for 81% of all potential shortfalls. There were only a small range of shortfalls where you'd be off and you didn't have the fuel or the time combined to get back to Mercury into the orbit you wanted to get into. And we also, as I mentioned before, we got to know those thrusters well, the main thruster for orbit insertion. So the key techniques for orbit insertion that were unique to orbit insertion, we actually practiced with some of the other maneuvers, how you rotate the spacecraft and all that. And, okay, go ahead next. Oh, by the way, on the recovery options, some of those were involved another 5 to 7 flybys of Mercury just to get back into the right orbit. So some of them were quite complicated. The orbit insertion and initial Mercury orbit look like this. Basically, a highly elliptical orbit, 200 kilometers to 500 kilometers at the minimum, and around 15,000 or so kilometers altitude at the maximum. And it was around an 82 to 84 degree orbit inclination. And you can see in the light blue that the entire orbit insertion maneuver was observable. Next. A design challenge after Mercury orbit arrival. We wanted to find amazing new science opportunities that no one ever thought of, even sometimes during orbit while we were on our way to Mercury. And it was, anyway, so initially we had planned this, I explained the basic orbit, and we had 5 corrections for the orbit and 1 year in orbit around Mercury. That was our basic plan. We're 7.6 year mission on the 8-year design life of the spacecraft. Well, we added another 3.1 years to that, and after 1.1 years in orbit, went into the 8-hour orbit. So now we have 50% more opportunities per day of flying by around Mercury. And we're ending the mission late in April of 2015, assuming things go well with the upcoming maneuvers. We have like a hover campaign coming up, which I'll talk about in a moment. We answered questions on potential water ice in the permanently shadowed craters. We added comet observations of Encke, a short period comet, and Ison, which I'm sure you heard about. The observation of Encke was from as close as 9 to 10 times the Earth-Moon distance, which is close on a planetary scale. And almost 250,000 images have been returned from Mercury orbit. And there's also an amazing science planning tool called SciBo Box, which we'll talk about in a moment. Next. So here's a look at the orbit progression. On the far right, the first orbit, that next orbit just to the left of it, it says XO1 start. That's where the mission would have ended had we not gotten any extensions. But instead, we went all the way around, and we're almost to the last orbit, which is just over 8 1/3 hours. And you can see the primary extended 1, extended mission 2, and extended 2 prime. And those are 1 2-year and 1/8 of a year mission extensions. And that last one I want to mention is not using much velocity change on the far right, just 12 meters per second. But we are going down to 5 to 36 kilometer altitudes repeatedly for well over 100 orbits. Next. And then here's just a quick look, a highlight of water ice and polar deposits and some of the highlights of the findings. There's a big range on how, they don't know how deep the water ice is, but it could be anywhere from 10 trillion to 1 quadrillion kilograms. So there's a lot of ice on Mercury in the shadow craters. Next. And then just a quick look at some of the images. We have 431 images of Comet Encke. One in there is shown there, 280 images from Comet ISON, and the orbits of the comets are shown there. Next. And then the last thing here is the SciBo Box planning software. What this is it takes the science objectives, the planet, sun, spacecraft orbits, hardware and science constraints, puts this all through, and the other side comes out all your science plans, your upload, many of your commands that you upload to the spacecraft, and it sorts everything out and gives you a maximized science return. It's an amazing push of a button, wait 8 hours, and you've got your results for the whole rest of the mission. Next. And then a quick summary, things that we've gone over with a highlight of a postage stamp that came out in May 2011. So thanks very much.